Hey there, it's Shannon Magic Myers coming at you live from San Diego, California. I hope you're having a wonderful day. We will be starting chapter 4 now from the Susanna Epp book, Discrete Mathematics with Applications. We'll be looking at elementary number theory and methods of proof. So now we'll be looking at more familiar concepts through the lens of determining the truth or falsity of a mathematical statement. So let's start with the definition. 4.1 starts a three-section part for direct proof and counterexample. The first one will deal with integers, and then next time we'll be dealing with the set of rational numbers. So what we're going to be assuming is this: a familiarity with the laws of algebra. Now this is Appendix A from your text. Just in case, this isn't the best scan, but you can zoom in on these, all right? So these are all assumptions that we are going to be using, all right? So, there's stuff you've been working with for your whole math life, so they should seem pretty familiar to you. Now, the 3 properties of equality is the next assumption. So for all objects A, B, and C, A is equal to itself. If A is equal to B, then B is equal to A. And then if A is equal to B and B is equal to C, then A is also equal to C. Next assumption, there is no integer between 0 and 1, and the set of integers is closed under addition, subtraction, and multiplication. So closure just means that you perform the operation with 2 members of the set and you get a member of the set for your result. You use this a lot in linear algebra, so if you haven't had linear yet, pay attention to this. This means that sums, differences, and products of integers give you another integer. And remember that there are infinitely many quotients when you divide 2 integers. So where you will get things that aren't integers. Like if you divide 1 by 2, you get 1/2, which is not an integer. And divisibility of non-zero integers by 0, sorry, there is a missing part there, is undefined. So the set of all integers is not closed under division, that operation. Okay? All right, so now let's get to this next definition. This next definition gives us the definition about even and odd integers. So some integer n is even if and only if n equals twice some integer. An integer is odd if and only if n equals twice some integer plus 1. So symbolically, we have n is even. This is an if and only if statement, so it's true both directions. There exists an integer k such that n is equal to 2k. So that's math ease for even. N is odd if and only if there exists some integer k such that n is equal to 2k plus 1. Good so far? All right. Now, example 1. Assume that R and S are particular integers. Use the definitions of even and odd to justify each of your answers. So now here, let's go through a little bit more slowly than you might, because remember, we want to show things. So this is kind of a first step towards being able to do an actual proof, direct proof. So couldn't we rewrite 4 times r times s as something else? Good, beautiful. You can write this as 2 times r times s, right? That's just a basic rule of multiplication, right? So the second thing to think about is what? What is 2 times r times s? Good. It's an integer. And why? Good, because the set of integers is closed under multiplication. So remember that z stands for integers, so the set of integers is closed under the operation of multiplication. Good. So, number 3, what would we say for a conclusion? We've been able to write this in the form of 2 times some integer, right? So I would say yes. Cool so far? All right, what about number 2? Is 6r plus 4s squared plus 3 odd? Well, could we rewrite this somehow? I mean, remember, for something to be odd, it needs to be what? 2 times some integer plus 1, right? So I want to get this where I have a plus 1. So isn't this equivalent to 6r plus 4 times s squared plus 2 and then plus 1? So I just changed the 3 into 2 plus 1. Now, with this, if I consider this portion of it, couldn't I factor out a 2? And then I would get 3r plus 2s squared plus 1 plus 1. So now all I need to do is establish that what's inside those parentheses is an integer. So let's start with 2s squared. Isn't that equal to 2 times s times s? What else do we need to consider? We need to consider 3r, right, belong to the integers, the set of integers, since the integers are good, closed under multiplication. And we were given that r and s were integers in the premise. All right, so we've got those 2 portions of it. Now let's look at the third. So, looking at 3r plus 2s squared plus 1 belongs to the integers, since the set of integers is closed under addition. You add integers and you get an integer out. And so what would our conclusion be? We have something in the format of 2 times an integer plus 1, and so we would say yes. 6r plus 4s squared plus 3 is odd. Cool, cool? Aren't you guys having fun? This is awesome. All right, so next up, another definition. This one deals with prime and composite numbers. So an integer n is prime if and only if n is greater than 1 and, this is an and statement, for all positive integers r and s, if n equals r times s, then either r or s equals n. And integer n is composite. If and only if, for n greater than 1 and n equal to rs for some integers r and s, with 1 less than r less than n and 1 less than s less than n. Symbolically, for all integers n with n greater than 1, n is prime if and only if, for any positive integers r and s, if n equals r times s, then either r equals n and s equals, what would it have to be? Beautiful, 1. Or r equals 1 and s equals n. N is composite if and only if there exists positive integers r and s such that n equals r times s and what? 1 has to be less than r, less than n, and 1 less than s, less than n. So you've got two integers r and s where both of them are between 1 and n. They're integers between 1 and n, right? Okay, so assume that r and s are particular integers. Use the definitions of prime and composite to justify each, I'm missing a 2 here, justify each of your answers. Okay, is 1 prime? So this is kind of a so easy it's hard one, right? The answer would be no, since 1 is not greater than 1, right? So we're all done there. Okay, so now look at number 2. If r and s are both positive, and remember they were given to be particular integers, is r squared plus 2rs plus s squared composite? Well, why don't we check out and see if we can factor r squared plus 2rs plus s squared. Isn't that equal to, beautiful, r plus s, the quantity squared. R plus s, the quantity squared. Now, what were we given? We were given that r and s were both positive, right? Positive integers. So that sum has to be what? Greater than or equal to? What do you think? Well, the first positive integer is 1, right? So wouldn't it have to be greater than or equal to 2, that sum? And that's since r is greater than or equal to 1 and s is also greater than or equal to 1. So neither r nor s is 1. Do you see that? Therefore, their product, the product of r plus s times r plus s, is not prime. Well, if it's not prime, then what would you think it would be? It would be composite, right? So we're going to say yes, because it was asking if under these conditions was this expression composite. Okay? Cool, cool? All right, proving existential statements, right? We're not called upon to do this very much, but just so you know how, recall that a statement in the form, there exists an x which belongs to some domain D such that q of x. Now that's true if and only if q of x is true for at least one x in the domain D. One way to prove this is to find an x in the domain that makes q of x true. Or you could provide a set of instructions for finding such an x. Both of these methods are called constructive proofs of existence. Okay, so please prove the following. There are distinct integers. Now notice the word distinct. Integers, m and n, such that 1 over m plus 1 over n is an integer. So distinct means that they are not the same. M is not equal to n. So what do you think? Now what numbers are in the set of integers? Good. It's basically the counting numbers and their opposites and 0, right? Make up that whole set of integers. So anytime you add a number and its opposite, what do you get out? Beautiful. You get out 0, right? So if we let m equal to 2 and n equal to -2, we have selected values of m and n that are two different integers, right? And if we have 1/2 plus 1 over -2, that's equal to 0, which is also in the set of integers, right? And so we've shown that there exists at least one, and so we're done. All right, how about the next one? There is an integer n such that 2n squared minus 5n plus 2 is prime. Well, what do you think we should do with this one? Let's check out and see if we can factor this, just to make it a little easier. So this is equal to, and you do need to have your factoring skills, the quantity 2n minus 1 times quantity n minus 2. If you're a little bit rusty on factoring, if you go to my, it's either called Introductory or Beginning Algebra site, in like section 6.5, I think, that video gives you like an overall picture of factoring. You can always review that if you want. Okay, so anyway, 2n minus 1 times n minus 2. Now remember, in order for something to be a prime number, one of the factors needs to be what? One, and the other one needs to be a number that can't be written as a further product, right? And both of them have both of the factors and the number, number that you get has to be greater than 1. So to recap, we need to find an integer, all right, where we get a product where one of the factors is 1 and the other factor is a number which can't be broken down anymore. It can't be written as a product other than times 1. All right, so let's take a look. Well, if we tried, remember you have to find your factors each have to be like one of them has to be greater than or equal to 1, and one of them has to be greater than 1. So if I did n as 0, I'd get a negative on each, so that's not going to work. If n was 1, I would get a negative on one of them, so that's not going to work. What about if n is 2? I get a 0 for the second factor. So if we try n equal to 3, let's see what happens. We would get 2 times 3 minus 1 times 3 minus 2. That is equal to 2 times 3 is 6, and 6 minus 1 is 5, and that can't be written as a further product, right? Except for 5 times 1. And I'm talking about within the integers greater than 1. So the other one is 1. And so by definition, this is prime. So we have found the existence of an integer that makes this true. Okay? Now, most of the time we are dealing with, so I guess we could do kind of a check mark on these. Most of the time we're dealing with universal statements, okay? And so one big thing that, you know, can be difficult to find is a counterexample, especially in linear algebra. People have some trouble with that. So this is the first part of universal statements, and then we'll be looking at how to prove universal statements using a direct proof. So to disprove a statement, you must show that it is what? False, right? So if you, to disprove a statement in the form of for any x in D, some domain D, if P of x, then Q of x, right? Well, you keep P as true, right? You provide objects, we'll call them, that are in the domain that make P true, and then show that Q would be false, right? So we need to show that the negation is true. There exists at least one that makes it a false statement. It makes the conclusion false. So you just need to show that that negation is true. And remember, a negation of a for any is a there exists. So since we only need to provide an example to show that an existential statement is true, the example provided to show a statement is false is called a counterexample. All right, please disprove the following statement by providing a counterexample. Now, this one is kind of taking it easy on us because a lot of times we don't know if they're true or false. We have to decide if they're going to be true all the time, or we have to find a counterexample to show they're false. So that is really often what people find difficult in this whole proofy world. But just kind of hang in there. We're learning all of these techniques, which are going to be your proof tools, and you want to be comfortable with all of them. So please disprove this statement. For all integers m and n, if 2 times m plus n is odd, then m and n are both odd. All right. Well, this is basically saying for any m and n, all right, that has an odd sum, then each of those summands, the terms, right, has to be odd. Okay? So sometimes it's useful to write out what that statement is in math, right? So for any m and n which belong to the set of integers, if 2m plus n is odd, then m and n are both odd. So what would the negation of this statement be? Well, there would exist an m or n, right? It'd be an or statement that belonged to the integers where if 2m plus n is odd, so you want to say that this first premise is true, you want to show that the conclusion is false, right? So there exists some m or n where they have this odd sum, but you would say M or N is even, right? Or not odd, right? Okay, so let's find one. Remember, we want the sum to be odd. So for something to be even, right? Let's see. We want the sum to be odd, and we want to find at least one even integer to plug in for M or N. So why don't we let M equal to 2? And we can let N equal to, I don't know, what do you want to let it equal to? How about 1, right? What are we going to have? We would have 2 times 2 plus 1 for our 2M plus N equals 5. So you've provided a true premise, right? But M equals 2, which is even. So we have shown by counterexample that the statement, the entire statement is false. Because for any statement has to be true for everything for it to be true. You just find one counterexample and it's false. All right? Okay, so proving universal statements. This is something that will be very typical. So the most common statements to be proved in math are universal statements. Now, notice that when we were proving existential statements, right, meaning there exists, right, we were just finding actual integers, right, and plugging them in to show, hey, there exists one. And people often and we did the same with counterexample. We found actual members of the set of integers to show that given this true premise, we had a false conclusion. So when you prove universal statements, you're not putting in actual members of the set. You're picking these arbitrarily chosen elements of the domain. And so what we need to do is we need to name them. So long story short, do not use actual members of a set. Use variables that represent members of the set in these direct universal statements. Unless we are doing method of exhaustion. This is not very typical, and it's only if you have a finite number of options here. In most cases, this method can't be used as there are often infinitely many ways a statement can be true. So, I mean, if you think about the sum of any two odd integers is even, I mean, can't you come up with true statements all day long? So I'm going to emphasize, the more typical ways. And one of them is method of direct proof. So these are some steps. You express the statement to be proved in the form for any x belonging to the domain. If p of x, then q of x. Start the proof by supposing x is a particular but arbitrarily chosen element of the domain D, for which the hypothesis, member P of x, is true. This is often abbreviated as suppose x belongs to the domain and P of X. And then you need to show that the conclusion Q of X is true by using definitions previously established results and the rules for logical inference. Okay? So, one last piece, existential instantiation. We use this all the time. If the existence of a certain kind of object is assumed or has been deduced, then it can be given a name. So you can name it a letter, as long as that name is not currently being used to denote something else. You don't want to name them the same thing if they are representing different quantities or different members of a set. All right, so the next 4 problems are, we have to decide whether each of these statements is true or false, and then justify our answers with either a proof or counterexample. So, number 1, the sum of any 2 odd integers is even. So, let's get started. We talked about what odd looks like in math, right? Now, this one doesn't say 2 distinct odd integers, right? And so, they could be the same, right? But we're going to kind of set this up as if it's different. And from the way I'm talking, you can probably see that I think this is true. And you can sort of check this in your head, right? I mean, isn't 3 an odd integer? And 5 is an odd integer? And isn't 3 plus 5 8, which is even? Right? So I think it's true. But I don't want to use 3 and 5 because there's infinitely many ways this can be true. So, what would we do? We could say there exists an R equal to 2n plus 1 and an S equal to 2k plus 1 such that n and k belong to the set of integers, right? Now, what would we say about R and S? Good. R and S are odd. And why is this true? Well, by definition of odd, and we won't put it, but the set of integers is closed under addition and multiplication. All right, so next up, we've got this going on. Well, what do we need to do? The premise is saying that the sum of any 2 odd integers is even. So premise is sum of any 2 odd integers, and the conclusion is, hey, these 2 integers will be even. No. The premise is what? If I add 2 odd integers, then my sum is even, right? So if we wanted to reword this, I would say if R and S are odd integers, then our plus s is an even integer. Okay, so let's take a look now. We have created the situation where r and s are both odd integers. If they were supposed to be distinct, we would have said that n was not equal to k, but they didn't say distinct, all right? So we're not going to exclude anything. So r plus s is going to equal to what? Good. 2n plus 1 plus 2k plus 1. And then we can put this for now. This is by substitution. As we go on, you won't be writing that in. But yes, you do need to document why things work in this class. Now, if I commute the numbers, because remember, the set of integers is commutative, I'll get 2n plus 2k plus 1 plus 1. And the set of integers is commutative. And that's under addition, because we were adding. All right, well, this ends up being what? 2n plus 2k plus 2, just by adding the 1 plus 1. So what would I do next? Well, if I factor out a 2, what will I get? N plus k plus 1, right? Which is an even integer. Isn't that groovy? And that is an even integer by definition of even integers. And we're done. We did our first proof, first real proof. Okay, good so far? And those 2 lines are just showing I'm done with the proof. Sometimes your books, you'll see put a little box. Sometimes they'll do, other notation. Sometimes it's just a period. Okay, so now if n is any odd integer, then -1, that quantity raised to the n, equals -1. So what do you think? Well, let's try some out, right? -1 to the 1 is -1, that works. -1 cubed is -1, so that works. I think this is true for all odd integers. So keep in mind that if you had a negative integer, you would have 1 over -1, that raised to the positive, remember? So let's put this as a note. -1, I'll just say raised to the negative n is 1 over -1 to the n. And so you would still get, this proof would account for that. Okay? All right, so let's get started. I think this is true, so I'm going to write the proof. It's already in terms of, an if-then statement. So let's check it out. What have we been given? We've been given in our premise that n is an odd integer. Well, since that's true, there exists some k such that, remember this means such that, the backward epsilon, such that n equals 2k plus 1. So we have -1 raised to the n is equal to what? Beautiful. -1 raised to the 2k plus 1. The premise for that would be awesome. Substitution. Next up, we would say that this would equal to, remember your laws of exponents, -1 raised to the 2k times -1 raised to the 1. That one, you can either call them laws or properties of exponents. Okay, so we're getting there. The first part, we could say, again, by properties of exponent, that would be -1 squared raised to the k. And then -1 to the 1 is just -1. So that first part is, again, properties of exponents. All right, well, what comes next? -1 squared, the quantity squared is just 1. And then we would get 1 to the k times -1. Well, we're not sending k to infinity, so this is just going to be 1 times -1, which is -1. And so we're done. We have proved it, proved our statement. Groovy? Awesome. Next up, what do you think? The product of any even integer and any integer is even. So what does even mean? Even means that it can be written as 2 times some integer, right? So let's check it out. What if your integer is 4, right? For your even integer. And let's try another even. 4 times 8 is 32, which is even, right? Because you could write that as 2 times 16, so that works. How about an even and an odd? So 4 times 5 is 20, right? Which is even. So I think this is true. So let's take a look. This one really isn't in an if-then form, right? So what is the if-then way to write it? If you tell me, you can do it. An even integer and any integer are multiplied then the product is even. Cool. All right, well, let's move on with our proof. All right, so proof. We need an even integer and we need any other integer, right, to serve as our basis. So let n and k belong to the integers and let r equal to what? 2k. So we know R is even by definition, right? So let's see what we have. R times N is equal to what? Beautiful. 2K times N, and that's by substitution. Well, that's going to equal to 2 times K times N. And why is it I can do that? Because set of integers is associative, right? And this is even. And that's by definition. Cool so far? Awesome. So we're done. We've done it. All right, so our last one here, what do you think? Oh, sorry, there's a typo here. For all integers n, if n is prime, then -1 raised to the n is equal to -1. What do you think? What's the first prime number? Be careful. Right. Isn't 2 the first prime number? I mean, let n equal 2. Two is prime, right? So then -1 squared is +1. So we have shown by counterexample that the statement is false. It only needs to be false for one thing, okay? So we're done with that. We've shown it's false by counterexample. And guess what? That is all for this lesson. So if you like what I'm doing, please subscribe. If you'd like to see some other movies, let me know and I'll do my best to make them for you. And I hope you have a wonderful morning, afternoon, or evening whenever you are watching this show. Bye.